Hello, everyone. So today I'll be talking to you about my ongoing work, which I'm doing with Anuj, Samanvay, Prayush at ICTS, and Kaushik and Chandra at IIT Madras. And it's on using our recently developed eccentric waveform model called ESIGMAHM to search for signs of orbital eccentricity in the already detected gravitational wave events that we have. So, okay, why would we like to detect orbital eccentricity? This is something that I'll explain in the next 2, 3 slides. So, during its 3 observing runs, LIGO Virgo have observed about 90 gravitational wave events. And as we know, these gravitational waves are being generated due to the gravitational wave driven in spiral of compact objects, which we believe are black holes or neutron stars. So this obviously means that these binary systems are forming in the universe, but not only are they forming, they are merging within the age of the universe so that we are seeing their mergers. Now, it turns out that gravitational wave emission and the energy loss due to it depends very strongly on the orbital separation of these objects. So unless they have had very small orbital separations of the order of tens of solar radii, it turns out, if you do a back of the envelope calculation, that they won't merge within the age of the universe uh, due to a gravitational wave assisted in spiral alone. So how exactly these compact objects come close enough to form binaries and then ultimately merge within the age of the universe is still an open question. So basically, two main binary formation channel categories have been proposed. The first one is called the isolated binary formation channel, in which you start with two stars. The heavier of them then starts to swell up in its lifetime. This is something known as the red giant phase of the star, in which it swells up to thousands times of its original radius. And then it starts transferring its matter, the outer envelope, onto the smaller star. And then what is left of this star is just its core, and then it undergoes supernova and becomes a black hole. Now after some time, the second smaller star undergoes the same process, becomes a supergiant, then transfers the mass onto the black hole. And it turns out that during this particular mass transfer, uh, the orbit shrinks, and it shrinks enough that now these two objects start moving in the gaseous environment of this mass that was being transferred by the smaller star. And it is because of the motion of these objects in this gaseous environment, that drag due to this gaseous environment makes them lose energy and tighten their orbit. And ultimately, the second star also undergoes supernova and becomes a black hole, and you get a very tight orbit of black holes. So this is this particular formation channel. After this point, gravitational wave assisted in spiral can drive them to merger within the age of the universe. Now, if this is actually happening in the universe, what are the expected properties of the black holes that we expect? Well, first of all, you can expect, due to these mass transfers, that they will have spins aligned with each other. However, there is no consensus on it. People say that there may be slight misalignment because during the formation of supernova, they may receive a kick, which may slightly misalign their spins. But one thing for sure that will happen is they won't have any detectable orbital eccentricity in them, because the binary black hole that is formed at this stage has enough time, enough cycles to go through, that gravitational wave back reaction onto this orbit efficiently circularizes the orbit. However, in the second type of formation channel that has been proposed, this may not be the case. In this, what happens is there are dynamical encounters, three body encounters basically, which may tighten the orbit of the binary. So, for example, there are multiple ways I can explain one of them. So, you may have a binary. The third object may come and may tighten its orbit by sapping away the energy, and thus leads to a very tight orbit. In this case, what are the black hole properties that we can expect? Well, first of all, you will expect isotropic spin distribution, because these are very random collisions, random interactions. So you won't expect any preferential alignment of spins. Second, there may be detectable orbital eccentricity in them, because these in spirals, these black holes are formed so close to each other that they don't have enough time to radiate away their eccentricities due to gravitational waves. So therefore, eccentricity is important. If we detect an eccentric merger, it will be a smoking gun signature of a dynamically assembled binary, and we will learn a lot about how these black holes form in the universe. Now, how science using gravitational waves is done is basically by comparing the LIGO data, which is very noisy and is shown in blue and orange here. And we compare this LIGO data with theoretical template waveforms, which are generated through what are known as waveform models, uh, to estimate the source binary properties. So basically, we match the waveforms which are produced by our understanding of the theory of gravity, and we can predict, given some masses and spins of the black holes, what we expect the gravitational wave signature to look like. And this is shown in black. And then we compare and match it with the data, and we then figure out which one matches the best. And we say that the properties corresponding to that best matching template must be the properties of the black hole. There has been no confirmed eccentric gravitational wave detection yet. And even to do so, we will need waveform models which have eccentricity in them. And E-sigma-HM is one of our own developed model, uh, which is an eccentric model for aligned spin binary black holes. And it also has things like higher order gravitational wave modes, and it's an in-spiral merger ring-down waveform model. Its in-spiral piece is constructing using state-of-the-art post-Newtonian theory results and self-force results. And the merger ring-down piece of this, which is the very end part of the waveform, is a quasi-circular piece, which comes from a numerical relativity surrogate model. Doesn't matter if you don't understand these terms. It's basically a waveform model, eccentric waveform model. So we analyzed, this is an ongoing process, as I said. We have analyzed 63 LIGO events so far. And what I'm showing here is the eccentricity distribution for each of these 63 events. Basically, what these are, these vertical plots are, these are basically histograms. And I have symmetrized them just to make them look beautiful. These are called violin plots. So as you can see, and in bold, I have indicated some events which have been claimed to be eccentric by some of the previous analyses. But obviously, you can see that some of these posterior distributions on eccentricity are very flat. So you can't really conclude whether they are eccentric or not. So we need some statistic, some number to say whether they are eccentric or not. And for this, we basically do the analysis using a quasi-circular version of the same eccentric waveform model. And then try to compute the ratio of the evidence of the eccentric hypothesis as compared to that of the quasi-circular hypothesis by computing what are known as Bayes factors, which I am showing here, or rather their logs. If this value is between 0.5 to 1, we can say that this is a marginally interesting event and is in the support of eccentric hypothesis. But if it's above 1, we can definitely say that it's interesting. And so far, we have been observing only one very interesting event and three marginally interesting events. So I'll discuss some more about this particular interesting event, GW200129. Now, it seems as if nature is hell-bent on making our lives difficult, because it turned out that during the time of this particular event, uh, there was a glitch in one of the LIGO detectors called L1, the LIGO Livingston detector. Glitch is basically a spurt of noise in the detector, and this contaminates the data basically. And it turned out that it contaminated the data only below 50 hertz. So we performed analyses on this with multiple types of data sets. So it turns out that LIGO also publishes the deglitched version of this data, and the posterior with the deglitched version of data looks like this. As you can see, it is still showing some eccentricity. Then we also performed an analysis in which we took the LIGO Livingston data, but only above 50 hertz, because as I told you, this is contaminated below 50 hertz. And we also did not use any Virgo data, which is this V1, because this particular reference also suggested that there was some problem in the data with Virgo detector as well. But still, even with this data, although the base factor is not very high, we still see some posterior level evidence for eccentricity. Then we thought that, okay, let's reject both L1 and V1 data and just use the Hanford data, and then the evidence goes away. It turns out that this particular event was a very hot topic for uh, spin precession studies also. That is, it was shown by many analysis that this has significant evidence of being a quasi-circular precessing spin system. But this particular paper again showed that these claims are again highly contingent on handling the data of Livingston properly. So we are in the process of doing some analyses to thanks. So analyses to disentangle these two effects, the effects of spin precession and eccentricity. So I will conclude. So eccentricity is a very clear indicator of a dynamical formation channel of binary black holes, and if we detect them, detect even a single eccentric gravitational wave event, it will be a very important clue to the formation channel of these black holes. We analyzed about 63 binary black hole events using our waveform model ESIGMAHM. And this particular event shows some hints of eccentricity, but a clear evidence is muddled by the data quality issues. And we are in the process of running the analyses on all the binary black hole events. And the long-term goal is to uh, analyze even the current observing run events of LIGO, which is called O4 using E-sigma-HM in future. So with this, I will conclude. Thanks.
Any questions now? Rajesh.
In the beginning, you said that there are no eccentric models and GW hasn't confirmed any eccentric merger detection.
I did not say that there are no GW models. Ours is one.
Okay.
And there are many others also.
But
there is no consensus on the events that they claim to be eccentric. So some analysis will claim some events to be eccentric. Then the other analyses with a different waveform model will conclude that, okay, the ones that they said were eccentric were not eccentric, but we found some new ones. So there is no consensus in that manner. There is not a single event on which everyone concludes that yes, this has eccentricity.
I see. Okay.
Are there any more questions? Okay, I had a naive question. You showed that there was some glitch data, right? So how do they understand this part was glitched and the others were not?
So you can you expect, you know how the noise looks like in detectors when there is no spurious noise. So just by looking at the detector data and analyzing it, you can figure out whether it. Now there is a more interesting question to yours is there may be a glitch which can mimic the gravitational wave signal itself, and yes, this is not an easy problem. So in those scenarios where glitch mimics gravitational signals very well, it is very hard to disentangle.
All right, thanks. Okay, let's thank Akash then.